Right now, a machine built by human hands is drifting 24 billion kilometers away from Earth. It is moving through interstellar space, a cold, empty expanse well beyond the protective boundary of our Sun. When this probe launched on a Titan 3E rocket in 1977, engineers designed it to survive intense radiation for a 5-year primary mission. Today, that same 1970s hardware is nearing a half-century of continuous operation. The radio transmitter on board runs on 22 watts of power. That is roughly the same amount of energy used by the small bulb inside a standard kitchen refrigerator. Despite that faint output and the staggering distance, we are still successfully receiving packets of engineering and science data today. This connection challenges our understanding of signal propagation, raising a specific question: how do the physical laws of the universe allow a machine this old to speak to us from this far away? The moment that weak radio wave leaves the spacecraft's dish, it faces an immediate physical threat. In the vacuum of space, a signal doesn't travel in a tight, focused laser beam. It spreads out continuously in every direction. This is the inverse square law. As a wave pushes outward, its energy covers a larger geometric area, causing signal density to drop exponentially. Reaching Earth, it has degraded into a microscopic whisper. The energy impacting our atmosphere is less than 1/1,000,000th of a watt. To detect this faint signal, NASA relies on the Deep Space Network, a global array of massive 70-meter-wide antennas built to capture dying signals. Communicating with the most distant object in the universe is now defined by the sheer scale of Earth's brute force engineering. We rely on these massive dishes to amplify a signal that is otherwise physically indistinguishable from background noise. Even with those massive antennas, the physical distance creates a massive hurdle with time. Radio waves travel at the speed of light, but across 24 billion kilometers, a single message takes about 24 hours to arrive. Sending a command and confirming it worked requires a 2-day round trip. The spacecraft is also moving away from us at immense speeds, which stretches the physical length of its radio waves, a phenomenon known as the Doppler shift. Ground engineers have to constantly calculate and adjust their listening frequencies just to keep the receivers locked onto the signal. The physical alignment required over that distance is incredibly fragile. In 2023, Voyager 2 experienced a software error where its antenna drifted slightly off its target angle. The shift was just 2 degrees, but at those distances, 2 degrees means the signal misses Earth entirely. The probe sat in silence for weeks until a pre-programmed automated routine forced the spacecraft to correct its orientation. The combination of a 2-day time lag, extreme velocity, and the need for pinpoint accuracy makes every single transmission a high-stakes event. The margin for error is effectively zero. The external dangers of the interstellar medium are secondary to the internal reality of Voyager's own hardware. Entropy and power loss are the ultimate mission killers. This chart tracks the output of the spacecraft's radioisotope thermoelectric generators, nuclear batteries that convert the heat of decaying plutonium into electricity. Because the plutonium decays, the power drops slightly every year, falling from over 400 watts at launch in 1977 to the critical sub-200 watt level it operates at today. To keep the core communications and heating systems alive on this shrinking energy budget, NASA has engaged in a decades-long process of triage. They are permanently cutting the power to scientific instruments, letting them blink out one by one. Sometime in the next decade, the nuclear battery will decay past the point of minimum return. There will be no more instruments left to turn off, and the communications array will lose power for the last time. A loss of power does not mean the spacecraft stops moving. Long after the signal fades, this machine will continue to drift through interstellar space at over 17 kilometers per second. Bolted to its exterior is a physical payload built to outlast the electronics. It is a gold-plated record, carrying a curated selection of sounds, images, and greetings from a pale blue dot. Once the signal finally goes dark, the spacecraft begins its second life as a permanent artifact. It will drift through the galaxy as a physical archive, carrying the memory of humanity into a future far beyond the lifespan of its own electronics.